In our next example, we are going to prove that the sum, as I goes from 1 to n, of 1 over I times I plus 1 is equal to n over n plus 1. And I made a little note up here. This part that I put the box around is, we would call Pn, proposition n. And we're going to prove that's true for all n. And just for practice, let's make sure we can write this out without using the summation symbol. When I is equal to 1, this would be 1 over 1 times 1 plus 1. So when I is a 1, you get 1/2. When I is a 2, you get 1 over 2 times 3, which is 6. When I is a 3, you get 1 over 3 times 4, which is 1 over 12. And the last term would be when I is an n, you get 1 over n plus 1. And that's equal to n over n plus 1. This is another way of writing the proposition n, just without summations. And it's good practice to do that once in a while. Okay, well, let's prove this is true. Let's do the base case where n is equal to 1. I already did it. N equals 1. Well, if n is 1, you're only looking at this one time with I equal 1. 1 over 1 times 1 plus 1. And the right-hand side, since n is 1, would be 1 over n plus 1. They're obviously equal to each other. I went ahead and wrote 1/2 equals 1/2. We verified it. The base case works. Now, I wrote this one slightly differently this time. We want to prove that pk implies pk plus 1 for some arbitrary natural number k. So I'm just saying, I want to make it clear to the reader what we're going to do. Suppose this, which is p, that's proposition k, because I took proposition n and I just replaced n with a k, so I replaced all the n's with a k. So suppose that's true, and what do we have to do then? We have to prove that pk plus 1 is true. Pk plus 1 just says go from I equal 1 to k plus 1. The proposition, the expression, of course, stays the same, 1 over I plus 1. So we're just taking the summation one farther to prove that this is equal to, and this time k, we've gone one farther, so I have to replace k, each of those k's with a k plus 1. K plus 1 over k plus 2. So we haven't proven it, but that we've shown the reader exactly what we're going to do. Okay. So let's just go ahead and say now that but I equals 1 to k plus 1 of 1 over I plus 1. This left-hand side of it, we have to prove is equal to that. But what do we know about this? We know that this is equal to I equals 1 to k of the same thing plus whatever happens when we plug k plus 1 into this formula. 1 over k plus 1, k plus 2. Just like up here, if I wanted to go all the way to n plus 1, I would start off exactly like this. And then the next term would be, when n becomes n plus 1, it'd be n plus 1 times n plus 1 plus 1. 1 over n plus 1, n plus 2. That's where this came from. And by the induction assumption, the fact that we're assuming this is true, what is this equal to? K over k plus 1. Plus 1 over k plus 1, k plus 2. So all I did is I used the inductive hypothesis or the inductive assumption that those two things are equal. All right, let's see what we get now. Let's get a common denominator. I've got k plus 1 in both of them, so I need to take the first one and multiply by k plus 2 over k plus 2. So all I did is multiply k plus 2 over k plus 2 with the first fraction, plus 1 over k plus 1, k plus 2. And let's combine them into one fraction and get k squared plus 2k plus 1 over k plus 1, k plus 2. So I skipped an algebra step in my head. This is k squared plus 2k plus 1. And that top one's a perfect square, isn't it? Perfect square binomial, that's going to be a trinomial. That's going to be k plus 1 quantity squared over k plus 1, k plus 2. And I'll come back way over here, and I think we're done. Cancel out one of the k plus 1s, and we get k plus 1 over k plus 2, which is exactly what we needed to get. So we supposed pk was true. To prove that this one's pk plus 2. I'm sorry, pk plus 1. We supposed pk was true and proved that pk plus 1 is true.